This video is a response video to both the Mad Coder that codes at midnight, also known as Pyro, and Hythlo Day. Basically, what I'm doing here is I'm been learning Python and talking to Hythlo Day about economics. And what I'm doing here is I'm building the last economic model that Hythlo Day and I talked about um, in Python. Kind of answer some of the Hythlo Day's questions and to move forward in Python. So Hyperday's objection to the model was here when I changed the model from just being about myself and orange juice to being about goods in general, and this is all the goods in the economy and an aggregated demand curve. Um, and he says, you just can't do that. Each good needs its own supply curve. Each person needs their own demand curve, and rightly so. Um, So what we're going to do today is introduce a technique called the Lagrangian method of constrained optimization that can be used to solve this model, but can more importantly be generalized to multidimensional versions of this model. We're going to have Python find the point where supply equals demand, or that marginal benefit equals marginal cost. And I'm also going to find this box which maximizes the profit that a monopoly or other price setter would set their output of quantity of goods at. So here's the program in Python. I named it 1 by 1 by 1. And it's a huge improvement. In my last video, I was getting all kinds of stuck with trying to do calculus on functions. And in the Hangout, the Mad Coder was very helpful. Says, hey, you need to do SymPy, and what you need to do is use expressions instead of functions. And that was pretty much all I needed to know in order to make this awesome program. But and I sent him a note saying, hey, I'm on the right path, I'm doing good. But then he went and made a whole response video to all the sub questions I had asked in my last video about what does kwarg mean, kwarg mean, and he's like, oh, that means keyword arguments. Um, so I mean, I'm not using functions in this program. I'm using expressions, but um, functions are going to come up again. So I'm very happy to know things like what keyword arguments is, and things like keyboard shortcuts, and how to use strings. All this stuff that he's talking about is hugely important. So thank you again. So in his video, the Mad Coder talks about practicality. If we don't do we want to do all the math ourselves when there's already math programs lined up to do this, that will actually make the computer do the math faster, so that the practicality is both in terms of the programmer and the computer. Um, but I'm getting at something a little bit more deeper. There's a guy that posted a video about this kind of thing yesterday named Ben Lambert, and I'll post a link in the description to his video. It's an interesting video, so you might watch it. He's talking about doing data analysis, and that when you do a empirical study and it doesn't line up with theory, then it's the empirical study that's wrong. And he talks about that several times in the video, and it's an interesting concept. The first part of the program is to import the tools I'm using SymPy to do the math, and importing matplotlib in order to make a graph. The next thing I like to do when I'm writing a program is have a space where I can declare all my variables. We're going to have x, which is going to go along the horizontal axis, and that refers to like quantity of goods. And there's going to be y goes up the vertical axis, and that kind of refers to price. And then also we're going to have lambda and lambda to do the Lagrangian. we often need a bunch of symbols that stand for L. And lambda in Greek symbols is L, and lambda in Calrissian symbols is L. Now, what the Python code is doing is saying we use this string. A string is like, characters or text, um, and we use that as a mathematical symbol. The next thing I like to do in a program is have a little space where I can declare all the expressions I'm going to manipulate later in the program. Um, the first one here I call expr underscore util for a utility function. Now, at first I thought the expr underscore was necessary code, but it turns out it's not. I could have just called this utility and been fine. Now, utility function, as discussed in previous videos, is some scalar multiple times the square root of x. In this case, I'm using 100 as the scalar multiple, so it's 100 times the square root of x. And then I do it again. I say, give me the utility function again. But this time I say, hey, use this MathJax font, or whatever you call it, printing, and it makes it look really great. This is one of the things I really like about this Python notebook stuff. The next expression is a demand function, which is just the derivative of the utility function. And as you can see now that we're using expressions instead of the functions for this purpose, it works like a charm. So awesome. I'm really excited. The next expression is the total cost function, which in the last econ video we described as the fixed cost plus the variable cost times some power of the x. So in this case, we've got 4 as our fixed cost and 3 as a variable cost and 1.5 as the power. Now to find the supply curve, we need to find the per unit cost. So we're going to take an average, and so we're going to divide the total cost by x, which is the quantity. So when we plot the supply curve and the demand curve, this is what we get. It looks a lot cleaner than my original drawing, but not as many colors. Basically, the supply line is the blue line and the demand line is the blue line. I'll have to get better at plotting as we go on, but hopefully you can see how this is the same thing as what I was drawing before. So the first thing I'm going to do with the program is find the point where supply equals demand, marginal benefit equals marginal cost, profit is 0, and consumers benefit. It looks to be about 17.5, a little bit less than 17.5, and the first thing we're going to do is the method discussed in the last econ video, where we're going to set these functions equal to each other and solve it. To do this, we're going to need the solve command. Now, the solve command works, like you notice these expressions don't have the equal signs in them. The solve is going to solve the expression as if it was equal to 0, right? So right now I've got supply equals demand. What I want to do is I make this function called, or this expression called expression consumer utopia, which is basically when I have supply minus demand, then that equals 0. So the next thing I do is I'm going to simplify that expression. I don't think it's at all necessary, but it's a nice thing that SymPy can do. And so I just wanted to kind of take note of it. And then this is also the part where I found out that you don't need to write expr underscore, that you can just write the name of the expression and go from there. Next, I'm going to use the solve command, and it's going to put out the output at the bottom of the thing, and it finds 2 answers for this problem. The first answer is a very small answer, and it found it because basically both these expressions are infinite at 0, and so they're the same, and so it found that it's something very close to 0. Computers always kind of approximate things, and the next answer in the list is the one I wanted. It's about 16 and a half, just a little bit under 17 and a half. So that's what we were looking for. And it's also got this noise on it, right? It's a complex number. It's got the real part is the answer, and the imaginary part is the noise. It's just kind of a rounding error from the computer approximation. Um, at some point in the future, I might try and figure out how to take that and get rid of the noise. But the first thing I do is take it out of the brackets, which I'm going to use doing the pop command, which is just all it does is take things out of a list. Like if it's in a list, I can't do math on it. So I pop it out of the list. Now because I wanted the second answer in the list, I put pop 1 because Python always starts counting at 0. So we're going to do this problem and find the same point again, but then we're going to use the Lagrange method of optimization. Basically what this does is for method of examining phenomena, where we're going to ask what is it the phenomena wants and why can't it have an infinite amount of whatever it wants. So basically what we'll do is we're going to set up an objective function, which is what the phenomena wants, and then we're going to put in some constraints that stop it from getting an infinite amount. So, and basically what we're going to do is have it be lambda times the constraint, and the constraint is equal to 0, so that basically this is adding, lambda times 0 is 0. So we're basically not changing the function except for an infinitesimal amount. You can have more than one variable, you can have more than one constraint. So in this example, it's a function of x and y. We've got minus lambda 1 times constraint 1 minus lambda 2 times constraint 2. Now these constraints also have to be in terms of x and y. So then we've got 4 variables and they're all in one equation, so it's unsolvable. But what we can do is we can take the differential in terms of x and take the differential in terms of y and take the differential in terms of lambda 1 and take the differential in terms of lambda 2 and set those all equal to 0. And so then we've got 4 equations with 4 unknowns. And when we solve that system of equations, we will get our optimized values. Now, Hythloday optimized doesn't necessarily mean better. It just means maximized or minimized. I just thought I'd make that specific. So here back in the program, we're going to do the Lagrange method. First, we're going to set up the Lagrange function, our objective and our constraints. Our objective here is x. Basically, the consumer wants to consume a maximized quantity of the good, and it's going to be minus lambda times our constraint. And our constraint is that demand is going to be equal to supply, which is set to 0 by subtracting supply from demand, or you could subtract demand from supply. It doesn't matter. It also doesn't matter if you subtract lambda or add lambda, but the convention is to subtract lambda. Again, it doesn't really matter. That's just going to affect the infinitesimal, the rounding noise that the computer likes to do if you do plus or minus, but it's really not a big deal. Oh, and then also check it out. It put the actual symbol for lambda in the equation, which is cool. So then I'm going to use my diff command to find the differentials of the Lagrange function in terms of x, and then again in terms of lambda, and that will give me my system to solve. Of course, using a Lagrange to solve a one variable maximization problem is overkill, but we're learning the system. So then when we solve it, we get that same 16.5 number that we got when we solved it the other way. So now we're going to do a Lagrange one more time to kind of get the concept. What we're going to do is find this box that represents the profit that the monopoly firm would want to extract by reducing quantity. So for the objective function for this Lagrange, what we're going to want to do is maximize the area of the box and get as much profit as we can. So the area of the box is basically the bottom of the box times the side of the box. Now the bottom of the box is basically x. We're going to go across the x-axis, that amount, and then it's going to be multiplied by the height of the box is going to be the difference between the demand curve and the supply curve. Now this time it's going to be important that we have demand first, because at this, where the area where we're talking about this box is where demand is above supply, right? So we want to, the area is going to be that, or that height is going to be that distance between demand and supply. And then our constraint here is just going to be simply lambda times x, which just constrains x to be a positive number. Once again, we're going to take the derivatives in terms of x and in terms of lambda. So we get two equations with two unknowns and can solve the system. So what I'm doing to solve the system is basically using the method of substitution by using the dot subs command. And in the end, we get a output of 5.5. So in order to maximize profits, the monopoly is going to want to restrict output to 5.5 units. And there we have our problem solved. I'm feeling really excellent about being able to do the math in the Python, and I'm ready to move on to start talking about information theory episode 1, where we're just going to start talking about data analysis, which is really exciting. Oh, and for height today, at some point, we're going to do the some Lagrange with a 2x2 economy with two goods and two consumers and two firms. And we'll do that by hand so you can see all the mechanics of the Lagrange, because I think, well, I promised that we were going to do the unpleasant punisher model, which is, I think, my favorite economic model that I've come across so far. But I think to do that, we're going to need to be pretty good at the Lagrange. So we're going to do a 2x2 model with the Lagrange in it, so that we're ready to do. That'll finish off our the whole thing about equilibrium economics, and then the unpleasant punisher scenario. We're going to start moving into dynamic non-equilibrium economics, and should be pretty cool once we get there, but it might take a little bit of time still.